Welcome back. Today, we're diving into one of those small networking details that quietly shapes everything around it. In Lesson 4 of Stage 1, we're tackling MTU, MSS, and fragmentation, three closely related concepts that decide how big your packets can be and what happens when they're just a little too large. It sounds like plumbing, but these numbers are behind some of the most frustrating connectivity problems you'll ever troubleshoot. Here's the roadmap for the next few minutes. We'll start with MTU, the maximum size a link can carry in one piece. Then move to MSS, which is TCP's version of that limit. Once you account for the headers it has to wrap around your data. From there, we'll look at fragmentation, how it works, why it's generally something to avoid, and how IPv6 handles it very differently from IPv4. And finally, we'll get to path MTU discovery, along with the infamous black hole that can quietly break connections without ever throwing an error. So let's start with MTU, maximum transmission unit. It's simply the largest IP packet a given link is willing to carry in one piece, and on virtually every Ethernet network you'll ever touch, that number is 1500 bytes. Now, here's the key thing to internalize. That 1500 is measured at layer 3, meaning the IP packet itself. So once you subtract a 20-byte IP header and a 20-byte TCP header, you're left with about 1446 bytes for your actual application data. That gap between the link's capacity and what your app gets to use is exactly where MSS comes in next. But here's where it gets interesting. 1500 isn't universal. The moment you step off plain Ethernet, that number shifts. DSL users on PPPoE lose 8 bytes to PPP overhead, landing at 1492. Run a GRE tunnel, and encapsulation eats 24 bytes, giving you 1476. IPsec VPNs are even more variable, somewhere between 1438 and 1480, depending on the cipher. Data centers go the other way with jumbo frames at 9000, but only if every device along the path agrees, and IPv6 sets a hard floor. Every link must carry at least 1280 bytes, no exceptions. The takeaway: before you chase a weird connectivity bug, check your interface MTU first. It's often the answer. Now, MTU is the link's perspective, but TCP cares about something slightly different: how much actual payload it can stuff into each segment after the headers take their cut. That's the maximum segment size, or MSS. The math is straightforward. Take the MTU, subtract 20 bytes for the IP header, subtract another 20 for the TCP header. On standard Ethernet, that leaves 1460 bytes. On PPPoE, 1452. And on IPv6, because the header is twice as large at 40 bytes, you're down to 1440. The nice thing is, you don't configure this manually. Both sides advertise their MSS during the SYN handshake, and the connection quietly settles on whichever value is lower. But what happens when a packet shows up at a link whose MTU is smaller than the packet itself? The router has to split it. That's fragmentation. Picture a 3000-byte packet hitting a link with an MTU of 1500. The router carves the payload into chunks of 1480 bytes each, slaps a fresh IP header on every piece, and uses the offset field plus a more fragments flag to mark their order. The destination reassembles them using those offsets. But here's the catch: lose just one fragment, and the entire original packet has to be retransmitted. So when a router faces an oversized packet, it actually has a few options, and they're not all created equal. Fragmenting works, but it's expensive: extra headers, extra CPU, and that fragility we just talked about. The better choice is to drop the packet and send back an ICMP fragmentation needed message, telling the sender to try something smaller. That's the correct behavior when the don't fragment flag is set. The worst case? A misconfigured firewall that silently swallows the packet and the ICMP reply with it. The sender never learns, retransmits forever, and you get what's called an MTU black hole. IPv6 sidesteps the mess entirely. Routers aren't allowed to fragment at all. They must signal packet too big, and only the source can resize. And that signaling mechanism has a name: path MTU discovery, or PMTUD. Here's how it plays out. The sender fires off a full 1500 byte packet with the don't fragment flag set. It sails through R1 but then hits R2, whose outgoing link only carries 1400 bytes. R2 drops it and sends back an ICMP message saying, "Too big, try 1400." The sender takes the hint, resizes, and from that point on, 1400 byte packets flow cleanly all the way to the server. It's a quick negotiation that finds the bottleneck without anyone having to fragment. But that elegant negotiation depends entirely on one thing: that ICMP message actually making it back to the sender. And here's where things get ugly. Many firewalls, in a misguided attempt to harden the network, block all ICMP traffic. The packet too big notification gets silently dropped, the sender never learns to shrink its packets, and you fall into what's called a PMTUD black hole. The symptoms are maddening because they look selective. Small requests succeed, ping works fine, but anything that fills a full-size packet just hangs. The fix is straightforward. Allow ICMP Type 3 code 4 through, or have your routers clamp the MSS so TCP negotiates a safe size up front. That second fix deserves a closer look because MSS clamping is the workaround you'll actually deploy in the real world. The idea is simple. A router or firewall in the path intercepts TCP SYN packets and rewrites the MSS value downward, forcing both endpoints to agree on a size that fits. No ICMP required. On Linux, one ape tables rule with TCP MSS clamp MSS2 PMT2 handles it automatically. On Cisco iOS, it's a single interface command, IPTC adjust MLS, with values typically landing between 1360 and 1452, depending on whether you're tunneling through IPsec, PIPE, or plain Ethernet. But before you clamp anything, you need to know what the actual path MTU really is. And ping gives you a surprisingly elegant way to find out. The trick is the don't fragment flag with MDO on Linux and macOS, combined with a specific payload size. If the packet fits, you get a reply. If it's too big, the kernel refuses with message too long. From there, it's just binary search. 1472 works, 1500 fails. So you narrow in until you find the exact boundary. In this case, 1473 breaks, meaning the path MTU is 1500 since ping adds an 8-byte ICMP header. So let's pull the threads together. Remember these 5 anchors: standard Ethernet runs at 1500 bytes, jumbo frames at 9000, and IPv6 guarantees at least 1280. MSS is just MTU minus the IP and TCP headers, negotiated right in the SYN handshake. Fragmentation still works, but it's costly, so modern networks design around it. Path MTU discovery depends on ICMP. Block it, and you get silent black holes. And when tunnels misbehave, MSS clamping is your most dependable fix. To make all of this stick, here's your cheat sheet. One page you can come back to whenever a packet-size puzzle lands on your desk. The top half covers the sizes, MTU, jumbo frames, and how MSS is derived. The middle covers behavior, how IPv4 and IPv6 differ on fragmentation, what the DF flag does, and how PMTUD ties them together. And the bottom is your troubleshooting kit. Recognize the black hole symptom, then reach for ICMP Type 3 Code 4, or MSS clamping when ICMP just isn't an option. And that wraps up our deep dive into packet sizes. Up next, in Lesson 5, we shift from how much we send to who we send it to, exploring cast types: unicast, broadcast, multicast, and anycast. Each one answers the addressing question differently, and together they shape how traffic actually flows across a network. I'll see you in the next one.